Okay, we're ready. I believe that some people are still finishing transportation exam. Um, Yesterday, they asked me to put in Blackboard one of the all exams that we were talking about. So I already did yesterday. And so today I'm going to go over this exam was from exactly a year ago. Please turn your microphone off. So I would say that this exam is from almost a year ago. And the very first thing that you need to do, as we already discussed yesterday, we need to determine if this is a determinate or indeterminate structure. So in here, it's very easy to find out because we have two possible components, three possible, so we have five, let's do seven. Seven minus three equations that we always have, 4 degrees of indeterminate. The other thing that we need to decide it, that is very important if there is going to be a lateral movement or what we call a side sway. So anybody, I want you to look at this problem and tell me, do we have side sway, lateral movement, or we do not have? Anybody? No, no, no. Okay, no, good. Yeah, definitely no, because this is a pin. A pin will not allow the displacement either to the right or to the left. If this were a roller, if this were a roller, even though that we know that it's indeterminate, it will move to the right or to the left. But since we have a pin, no lateral movement. So the first conclusion is indeterminate and no sign. So it's not going to go anywhere. Now we need to determine if we're going to use 4EI over L. And so if there is a pin on the same line, the forces, there is no sway. If there is a pin, visual, if there is a pin, definitely there is no sideway because a pin has constraint. And one constraint is up and down, and one constraint or restraint is left and right. So there's no way that it's going to move. But if I replace this by a roller only have one constraint that is up or down. So definitely it will move either to the right or to the left. Any other question? All right. So any structure with a pin will not sway. Well, it depends of the location of the pin, but in general, if there is a pin in the constraining a lateral movement, definitely is not going to move. Any other question? All right. So we need to decide now we're going to use 40i or 3i. And no matter what we do, the moment at A has to be zero because this is a pin. The moment at D has to be different than zero because it's a fixed support. And the moment at E has to be zero because this is a pin. So AB, 4 or 3i? 3. I'm going to put it in here. BC. BC, there is no loading right now, but this is a rigid joint and this is a rigid joint. 4. So 4EI over L. CD, this is a part of a rigid joint and this is a fixed support. What are we having here? 4. 4EI over 15. And most of the mistakes come with people not looking carefully, and instead of 15, they put a 10. And finally, CE, rigid joint and a pin, 3. I'm going to write the distribution factor, just the equation from joint B. At joint B, we have two members framing into this joint, a column and a girder. So there are two different stiffness. I'm going to say distribution factor from B to A equal to 3EI over 10 over the summation of all the stiffnesses of the member framing into this joint. So it's the same number plus 4EI over 10. So 3EI over 10 plus 4EI over 10. And this computation, just to give you an idea, I'm not going to do all of them, is the 0.43. And the distribution factor from B to C is 1 minus that, 0.57. So we do the same. We do it for joint C. For joint C, we have to have three of them, CB, CD, and CE. And of course, joint D doesn't distribute anything. The distribution factor is 0. And joint A, the distribution factor is 1. But since we're using 3EI over 10, nothing will come to here. So the fixed moment is the one that is interesting. Since we had a side of this girder that will resist a moment, and we have one that doesn't have a moment. So we only had fixed end moment from C to E. So we only have fixed end moment from C to E. From E to C is 0. So whenever we look at our table, this has already been computed for you. So this has already been computed for you. This is a straightforward, you get this from the table. Or if you want to do it from here, you put equal and opposite, send 50% across. I have computed this for you two different ways. So on the next page, and everybody should have a copy of this already. On the next page, I show the computation of the distribution factor at joint B, at joint C, and also P and moment CE. And I use the formula on the left-hand side, and I determine minus 277.78. I say, or you can use the tables on the left-hand side, and we put equal and opposite and 50% to the other side, exactly the same. So I did the computation of the fixed moment just to show you how it can be done. I just got this formula directly from here. This is always A and this is always B. Always letter A, letter B. The second computation, I put an equal and opposite and I send 50% across. The numbers are exactly the same. So the computation by using the formula directly or indirectly, it gave me the same value. Any question up to this point? So we had to prepare a table. And the table is going to have joint A. If we want, we don't put it in there because it's not going to get any moment. Joint E, if we want, we don't put it in the table because it's not getting any moment. Joint B definitely had to be there. Joint B, two members, BA and BC. Joint C, three members, CB and CD and CE. Of course, two distribution factors in here, three distribution factors in here, one fixed A moment that is negative because goes in the counterclockwise. And I had done that for you. I had included the table. So this is the table that we had. Like I was saying, if you want, you can leave this joint out because you're not gonna get any moment. If you want, you can leave this joint out because you're not gonna get anything. But definitely, we need to include joint B from B to A, from B to C, 0.43 and 0.57. Make sure that you do write the correct distribution moment in the correct box. So very easy to reverse this now. At C, we had three distribution factors and we only have one fixed end mod. So here I have no choice but to go directly to joint C. That's the only joint that is going to have moment right now. Minus 277.78 at the joint. I had to put an equal and opposite. I do have to put an equal and opposite because to be in equilibrium, the summation of moment at joint C has to be zero. So the equal and opposite moment is going to be plus 277.78. 46% come to this member. 31% come to the member. 23% comes to the member. I'm going to write those now. And this means equilibrium. So I need to look. This is joint C. I have put a moment in here. 50% is going to go to this opposite end. I have put a moment in here. 50% is going to go to the opposite end. I have put a moment here. Nothing goes to the opposite end because the carryover factor is zero every time that I use 3 I over L. So the opposite to CE is EC. Nothing goes to here. The opposite of CD is DC. So I need to send 50% to that. So the opposite to CD is DC. I'm going to do this. And again, you look at CD, the opposite DC, I have to send 50% of the moment because the carryover factor is 0.5, that's plus 43.06. Anybody, any question why I'm sending 50% to DC? DC is a fixed support. I need to send 50% from CB to BC, the opposite end. That is plus 63.89. Any question about this? So I'm balancing joint C. Joint C had a negative to the entire joint. I had to give a equal and opposite, 46% comes to here. Whatever I put in here, 50% goes at 31% comes to here. Whatever I put in here, 50% goes at 23% goes to here. However, because this is a pin, nothing goes to here. This means that this joint is in equilibrium. C is always in equilibrium because it is a fixed support. So my first cycle, I had this joint that was not in equilibrium. I put it in equilibrium. Whatever I put on this side, 50% went up. Whatever I put on this side, 50% went up. Whatever I put in here, nothing goes to the opposite end because we're using 3EI over L. This is the first cycle of our moment distribution. This is an equilibrium. This is always an equilibrium because the fixed support B is not in equilibrium. So you can see that joint B right now, the entire joint, BC is the one that had the moment, but the entire joint, the summation of moment has to be equal to 0. So I need to put a negative 6389. 43% comes to here, 57% comes to here. And those numbers here minus 27.47 minus 36.42 and equilibrium. I have balanced this joint. So what I have done, at joint B, I have put a moment distributed between this column and this girder. Whatever I put at this end, nothing goes across because this is a pin and this is 3 over L. Whatever I put in here, 50% goes to the opposite end because this is a moment resistant joint and this is 4EI over L. This is joint B. Member BC, the opposite CB, minus 18.21. How much do I send to this end? How much do this go to this end? 27.47. How much do I need to send to AB? Anybody? 0. Because it's 3EI over L. If I use 4EI over L, that I shouldn't use because it's too much work. If I use 4EI, I need to be sending back and forth, back and forth, back and forth until I finish with 0. So that's the difference between a 4EI and a 3EI. The 3EI recognizes that the moment at A is 0. Every time that we go through one cycle, distributing the moment becomes smaller and smaller. Joint C that had 3 members had a minus 18.21. 46% are a plus 18.21 because that means equilibrium. 46% comes to here, 31% comes to here, and 23% comes to this side. I'm going to copy those numbers for you. I have put this joint in equilibrium. What I've done physically, I joint C. I have put some moment in here. I have put some moment in here and some moment on the other side and distributing the moment around this joint. Whatever I put in here, 50% goes to the opposite end because they carry over back to this one. Whatever I put in here, 50% goes to the opposite end because also the carryover factor is 1/2. Whatever I put in here, nothing goes to the opposite end because I'm using 3ei over L. Whenever I use 3ei over L, the carryover factor is 0. So going back to the table, I need to put from CB to BC goes 50%. That is plus 4.19 to DC goes 50%, and that is 2.82 plus 2.82. Any question up to this point? So what I'm doing, I'm balancing the joints. I'm putting the joints in equilibrium. In the thermal structure, all the members help resisting the load. All of them, they had the shift. As long as they had the ability to resist a moment. Fixed support, rigid joint. The only joint that is not in equilibrium right now is joint B. The entire joint needs a minus 4.19. And like I was saying before, every cycle that we distribute the moment, the remaining moment becomes smaller and smaller until it almost goes away. So 43% of plus 419 comes to here. 57% comes to here. I'm going to write number minus 1.8 minus 2.39. And that line means that the joint is in equilibrium. This means summation of moments equal to 0. I need to send from BC to the opposite end, 50% of that, that is a negative 1.19. In the real world, this is small, but I want you to get to 0.1. So joint C that had 3 members that helping to receive the moment, the joint right now had a minus 1.19. So I need to put to the joint an equal and opposite to the entire joint. 1.19 positive, 46% comes to this side, 31% comes to this side, 23% comes to this member. All of them, they are plus. So this is going to be plus 0.55 plus 0.37 plus 0.27. And this means equilibrium. Again, to show you physically what I had done, joint C, this side has some moment given, distributed, this some moment, and this some moment. The entire joint is resisting the moment. Whatever I put in here, 50% goes to the opposite. Whatever I put in here, 50%, and from here, nothing. This is going to be plus 0.27. And of course, I'm rounding the numbers. You can do it up or down because 0.27 times 2 is not 0.50. And 50% of this little number goes to the opposite end, so it's plus 0.18. And you can also tell that 0.18 times 2 is 0.36. It's just an approximation. This is the best approximate method that we have. This is a small moment, but since I wanted everybody to have the same answer, I'm going to put a minus 0.27 to this joint. It's going to be distributed 43% comes here, 57% comes to this. So this is minus 4 and minus 0.10. Flip. And this is minus 0.07. See, this is a small number. I'm going to throw it away, and this is what I do. Whenever we go to 0.1 or less, we stop. Now we add all the moment. Our check, whenever we add all this moment, our check is that this and this equal and opposite. Summation of this moment has to be equal to 0. I'm going to add everything in here. This is 0, of course. This is minus 29.39. This is plus 29.39. They have to be equal and opposite. Equal and opposite. The other one is plus 117.31 plus, turn the microphone off, please. And minus 209.43. So all that I had done in here for joint C, I add everything, CD, everything, and C. Summation of this moment had to be equal to 0 or very close to 0 because I have been rounding off the number. And finally, EC, this is plus 46.4. And this is 0. During the exam, I find that people give me a moment when it's a pin or a roller. So you do have to be very careful during the exam because very common mistake that people send 50% to wherever it's not supposed to. And all the time, the moment should be 0 and you don't have 0. Any questions up to this point? You say the reason we don't have to find equilibrium with this is because it is a wall, correct? Yeah, this is a wall. It's always in equilibrium. It's always in equilibrium because the wall, in theory, it has to be able to resist an infinite amount of moment. Because if this rotates, it's no longer a wall. So a wall is like just stay. You just imagine the wall is like some of your friends that they always want everything from you, never give you anything. Just a taker. This is the wall. A taker, take, doesn't return. You give your textbook to somebody, doesn't return it to you. You give them money, they don't pay you back. That is a fixed support. It's just a taker. As much moment as it can. Never return anything. Any other question? Okay. So I had gone in detail because every single moment distribution is done in a similar fashion. So I've done all of this in detail. The second problem, I'm going to cut short. But I want to go also to show you how to interpret this result. I'm going to show you, for instance, member AB. I'm going to put it in here. And member AB is a column and doesn't have any load, because if we had any load in here, we need to put it in. And it's a 10-footer. So AB has to be 0, but BA is 39. The direction, negative. Good. Once you have put this in here, you forget about the sign. This tells you, the only thing that this table tells you, clockwise or counterclockwise. That's all that we need. Now forget about the sign. You already have the direction. To be in equilibrium, we have to have a force to the right and a force to the left. So these two forces, they are producing a couple. Force and a moment equal to this one. Apply moment about this point. It's going to be this force times 10 minus 29.39. So it's going to be the moment divided by 10. So this force is 2.939. But you can put it in, during the exam, you're exhausted. It's like you ran a marathon, you're exhausted. So sometimes you cannot do this in your head. But you see, this 4 times 10 plus 29.39 equal to 0, so you divide this by 10. I'm going to plot the shear and the moment diagram, even though that you already know it by heart. Remember, we assume that we rotate this in this direction, or you put yourself in here, left-hand side. I start with this. Force constant. And this area is 29. If I ask you, is this positive or negative? Some of you would say positive, some of you would say negative. Makes no difference. It is to the left of this cone. And we know in here, we know we need to look at this moment because we always plot on the compression side of the column or the beam. So this moment, if you look and you follow the direction of the moment, where is the compression, left or right? Where is the moment, left or right? This call. Anybody? Left, correct. So this value in here, 29.9, and this is. And it has to be consistency because this is on the left. 29.39 on the left, put me on the left. So this is the first diagram. And we do exactly the same for each one of these. We do exactly the same. These tell us if it's clockwise or counterclockwise. So I have done this for you. You can see how from B to C, B to C plus 29.39 clockwise. C to B plus 117.31 clockwise. The same as before, rectangular, but this is why you have to be careful. Look, the direction of this moment, put the compression on. The direction of this moment, put the compression on it. And we call this reverse curvature. And the same happened with this column. And this is the only one that had a load, member CE. So CE minus 209.43, kind of close. 46, look, 209.43, we had it here negative, and the moment 0, 0. So this is a very simple problem. And why it was simple? Because this is from last year. They had 2.5 hours, and there were 3 problems. Because we voted, there were 2 regular problems and a bonus. So obviously, this was designed for students to solve it quick. Because there were 3 problems in here, and one was a bonus. I asked them, you want two problems or three? Everybody said three problems. So they got three problems. But this was designed to be a very simple. Any question about it, this problem? So I just want you to look at this problem because since we were limited amount of time, the bonus that I put, I'm going to go directly to the bonus. Look, the vertical deflection under this load. Right? So I want you to look at this problem. The vertical deflection under this load. This is problem number three. Problem number three, problem number one. What is the difference between these two problems? Anybody, look at the problem carefully and tell me what is the difference? What is the difference between, not right now, you look at this problem physically. What is the difference between these two? The question that may no different right now. What is the difference between this frame and that frame? Nothing. So they are the same. This is exactly the same. This is exactly the same as this one. So number three and number one, the same height, the same member, the same look. So I'm gonna go now to problem. And I'm gonna make a copy real quick of this problem. I'm almost done. So in the future and the near future, because you almost done, your degree is approaching very fast. The first generation online engineer. In the future, they're gonna pay you to be observant. I want you to be observant because last year people were not paying attention. But I know that you pay attention. So this is a bonus. Look, 10 points, maximum 150 points in the final exam. The deflection under 100 kip, deflection under and vertical deflection, no horizontal deflection. What do I need to compute deflection? What do I need to do? Anybody just give a short sentence of what you have to do. Given, given low, dummy low. Okay, good. So I'm gonna copy this frame again. So we back to what you did in exam number 2. They give me low, dummy low. What do I need to do next? Yeah, give me an idea. To solve reaction. Okay. And why do I need the reactions? Why do I need a reaction? To find the moment. Okay. How many reactions do I have in here? Okay, section. How many reactions had A? Yes, anybody? And a D? And a E? Okay, good. So, and somebody says sections, I'm going to take a section. So these are the section that I need between A and B, one section, between B and C, one section, between C and D, one section, between C and the load, one section, between the load and E, another section, and the same section because of the same limit of integration. And how do I write my moment equations in here? How do I write my moment equation? Anybody? Where do I need to go to write my moment? To write my moment equation, where do I need to go? No, where in my exam I need to go to get all of these equations? First problem. First problem. Everything, know the table. First problem. Right? So, since this is the same problem, and I need to write equation. Now, I already had all the free bodies. I'm going to show you where the free bodies are. This is problem number 1. This is the free body AB, free body BC, free body DC, free body CE. I had all my free bodies, all my free bodies. So, going back to this problem. Right? I already had this free body. I have BC, CD, I have CE, all my free body. I'm going to put the origin at this location. I'm going to put the origin anywhere I want. I'm going to go back to it. Member AB, if I put my section in here and this is X, my large M moment is what? If I put my origin in here. And I is for section AB, 2.939x. Good. Right? So I already have everything is done for me. Now I want to ask you a very honest question. I'm not looking at your face, so I don't know what your eyes tell me. But Look, when you look at this problem for the first time, would of you would of you realize that this is the same problem that we had in this exam as problem number one? And would of you come to the conclusion that you already had this free body? Just tell me yes or no. Yes, honest. Maybe that's a good answer. That means no. So, no, sure. So that's good answer. Now, look, this problem is already being solved for you. And you know that you have to take sections, and you know that you need reaction to find the moment. Right? So if you know that this problem is solved for you, and you come back in here, and say, look, I had this free body, I can write my equation here. I had this free body, I can write my equation here. I had this free body, I can write my equation. Be careful that there is a moment. And in here, I had two equations. The one in here, very easy, 19.50x. And the one in here is going to be 80.5x minus 209.43. So if we had a free body, we already had a equation. However, a lot of people did not realize that this was an indeterminate structure. So they went ahead and computed some reactions. They assumed that some moments were zero, right? And some people started solving this problem again to try to find the reactions, or they decided to use, I'm going to use all of this, like we did for problem number one. And so the easiest way to solve this problem is to look at each one of these free bodies and write your equation. But this is the biggest problem. How do I solve? I need to compute little m, right? The little m is here. How do I solve this problem? Yeah, give me an idea. So I know. We're going to talk about AY91. Have to use reaction from dummy, right? Yeah. Can you divide everything by 100? Divide the values. Okay. Good. So number one, look. All of these structures are elastic. If a hundred at the same location as the one, if a hundred at the same location as the one is producing this moment, the moment produced by one, exactly this number divided by 100, the number divided by everything divided by 100. So we don't have to solve for another moment distribution because we only have one load and we computing the deflection at the same location as the load. So if I go with a moment distribution for one, it's the same as this divided by 100. So there's a question about AY. To find the moment in here, do I need AY? To find the moment here, do I need AY? No, because it's just AX times the distance. to find the moment in here, I need this reaction at this moment. To find the moment in here, I need this reaction, horizontal reaction, and the moment because the axial is not doing anything. The same in here, to find the moments, I just need this reaction times the distance, I need this reaction time. So I don't need the value of. So this was an easy problem because you already had all the free body from problem number one. The only thing that you had to do in here is divide the other by 100. And this is what I did in the next page. I'm not gonna go in detail in here, but I said in here, same as number one problem. How do you do the second one? How do you do the second section? Just a minute. Okay, this is a good question. Video. How do you do the second section, right? I imagine, I might be wrong, that you're talking about this section, right? Yes, okay. So we don't have to use all of this because internally, whenever we have BC, this shear force and this moment are at the joint. So I already transferred the effect of everything. So I don't have to use, now I'm using free bodies because it will give me exactly the same answer. So we don't have to use big section. Since we already have free body, the equation is gonna be the same. That's what I'm saying in here. Look, this is free body AB, BC, CD, CE. So the only thing I need to do is take section here, this section here, this take care of everything. This section here, one on this side, one on that side. So we just have to do the free body diagram. We don't need the section. Any other question? I mean, we don't need this big section. We're taking the boundary condition, we're taking this free body by itself. This is not an easy problem. When I tell the problem when I panic, I stop thinking this detail, just think that I'm running out of time. I think that Stella and anybody else, whenever you panic, just deep in, breathe in and out, in and out. If you are religious, pray. If you are a drug addict, go outside and get high, or whatever. But you have to, you cannot panic. You know, in the future, in our life, if we panic, we get killed. So you just have to relax. That's how much time to go outside. Oh, you're already outside. You're in your house. Okay, so you cannot panic when I'm giving you a Christmas present with it. This is the same as the problem number one. And this is the same as another problem number one divided by 100. So you just need to learn how to relax, not only for this sport, all the other. So, and you also need to know when to abandon a problem, right? Because this was a 10 point. And whenever you come to here, and using the free body that Bijo was asking, you know, this is what you told me before, 2.939x. I already have mine. I divide by 100. Look, this is little m. I had for BC. BC, the moment is 1463 times x. And I had 2939. And here divided by 100. Looking here, the moment is 9.2127 times x and 4606, and this is divided by 100. So all of this moment if you look at everybody, you told me before 2.939 times x. In here, 14.67x minus 2939. In here, we had 9.2127x minus 4606. In here, easy 1950x. And in here is 80.50x and plus 209.43. So this is very simple equation. And this is what I had done in here. I have written the equation and here divided by 100. I have written the equation divided by 100. I have written the equation divided by 100, and I had done the same in here. So the word thing in here is the integration, because we had to integrate for every single section. I'm putting here divided by 100, by 100, by 100, by 100. Right? So this is a long integration. This is the point when you should abandon this and move to the other problem. I do it by hand. I did everything by hand because that's the way I'm trained and it's good for my mental exercise or whatever. But when you set up this, it's time to move to the other problem and come back. You have time to finish this, and you can do this in your calculator. Most of you can do this in your calculator. But all of the sections, they have moments. So all of the sections, they have moments. So you have to have 5 sections. Integration between 0 and 10, integration between 0 and 10, between 0 and 15. This one goes between 0 and 5, and this between 0 and 10. Yes, exactly. You have to do the 5 sections. But like I said, it's a lot of work. When you set up this equation, you should go and finish the problem and come back later. Because even to put this into your calculator, it takes a lot of time. How much credit would we go if we get up to the integration? I don't know yet. It depends how many sections. It depends how good these sections are. It really depends. But you're gonna get most of the credit. If you get to this point and you leave this, you get most of it. Any other question? You know what? I sometimes I find interesting that you really want to know something that I still haven't decided. But if you get to this point and everything is correct, you get more. Any other question related to these or points or whatever? So I just wanted to show you that you do have to be observant whenever you get a. Now I'm going to move to problem number 2. What is the rules against choosing the section? The rule between any two loads, there is a different moment equation. And so you can see in here. And this question is for Bijou. Look, this is my moment equation for member AB. Look at this shape. How many equations do I need to describe this? How many different equations do I have in here? What is to describe this moment? How many equations? What is this? The equation of a line, one equation. So anywhere in here, you're gonna take it. Now look at member BC. Member BC. Between B and C, this is the moment diagram. How many equations do we have in here? Anybody? Now help me. Tell her that you need to go outside and relax. What is the equation? What is the equation of this? What is this? How do I tell you what shape? What is this thing here? Is that parabola? What is this? Line. So one equation in here. So only one equation here between this point and point, one section. One section between any two loads. Look, all of these are the loads. Any two loads, one section. I'm gonna look in here now. Look in here. How many equations do we have that describe the moment in here? How many equations? What is this? One. Only one section. Now I'm gonna go to here at the bottom. How many equations? This is the moment. How many different equations I have? How many different equations? You tell me. 1, 2, 3, 4, 50. How many equations? This is my moment diagram. 2. Right? This is one, the equation on one line, and this is the equation, different line, different slope. So I need two sections. One section here, another section. So between any two loads, this and this consider one section. This is also considered loading, one section. That's why so we don't have to plot for every problem. We don't have to plot the shear and the moment diagram. It happened that for problem 1 we did, but we don't have to. But we know that between A and B, because there's a joint with different shear forces, different axial forces. So between A and B, one section. Between B and C, another typical section. Between D and C, another typical. Between C and E, 2. Between the loading and the loading, 1. Between the loading and the loading, another 1. So that is the rule. But if you compare this with the moment diagram that I just finished showing to you, you can see why between any two loads we have to have a section. Any other question? Okay. So, and that's very important because in the exam, some of you miss one section. Some of you miss one section. And some of you also made a mistake with the limits of the integration. Right. It had to be consistent with the limit and with the section. Problem 3 is a deflection. Problem 3 is a deflection. Yeah, look, problem 3. Is that what you're asking? Stella, is what you asking? Problem 3, this? The deflection? Oh, okay. I need to ask somebody to help me because I'm losing my memory. How many problems did I tell you that we're going to have in the final exam? Okay. So that's your answer. Now, do you want to rephrase the answer now that you had that? Yeah, but I already told everybody, I don't know how many people we had here today. We count. We have 40. So I mentioned yesterday, and I'll repeat again because you know, I don't know, it's me or I don't know, but I want to clarify. There are two problems in the final exam. The bonus is going to be either deflection or rotation. The reason why I'm giving you deflection or rotation because most of you during exam number 2 have problems computing the deflection. That's where you lost most of you. Whenever we had a problem in the class that most of you are confused with deflection, I assume the responsibility. It was my fault. It wasn't you. That's why I'm giving you the opportunity to redeem yourself, and also I want to redeem myself. So I'm giving you the opportunity to get your point back. So the bonus is going to be either a deflection or a rotation. Now that we're talking about this, before I forget, because sometimes I get confused. The first problem is going to come from the material that I cover after the first exam or material that is covered in the last part of the semester. So give a wild guess. What do you think that the first problem is going to be about? What time was structure? Of course, man, I think you should go to Las Vegas when they reopen because you're very lucky. Okay. I don't know. I cannot tell you more because I'm old. My memory is not that good. I'm making an effort right now. I'm telling you problem number 1, problem number 2. Any other question in respect to the exam, anything? All right. So I'm going to go back to the next one. Look, number 2, 10 point. Again, to K of DF for each of these members. Okay, definitely. I would do. So like any other project. And listen, I need to tell you that if you need help between now and the final exam, just send me an email. Sometimes I'm not in my office, I'm doing something else, but I have plenty of time. Like any other problem, we have to count all the possible components of the reaction. Component of reaction, we have 3 and 2, 5 and 2, 7 minus 3, 4 degrees of freedom. First conclusion. The second conclusion is the most important one. Is there any possibility that this frame is going to sway, it's going to have lateral movement, it's going to have size? Any possibility? Hey, Nick. Next semester, Nick. Okay. I'm going to ask again. With this loading, is there any way that this frame is going to sway? Only Marisa said yeah. And now we had John also. We had 2-1. Who's winning? The yes or the no? Oh, 2 points. So how do you know there are 2 pins? And we're talking about, that's what I was very careful when answering before. Look, this frame, we're talking about this joint moving. This joint, because of this load, because of that lack of symmetry. We're not talking about this pin moving. We're talking about the top portion. It's like you moving your head without moving your feet. So due to the load, the question is, are we going to have any of these joints to move to another jet? And now I'm going to tell you something, right? No, because it's pushing left into the wall. And where is the wall, Jeremy? Where is the wall? BA? BA is not the wall. BA is the column, and the column is free. This top portion of the pin at A, pin A, would it will sway as long as the only way that it will not sway is you hire Superman or Superwoman to put the hand in there. That will be the only way if you stop this joint. If you put the force in there, right, it will not move. But I'm going to tell you another way. Right? Whenever we had doubt, it may not different. You pin at E. At E, well, that's different. You're putting another support. And putting a pin at E is the same as putting a port in here because the pin will stop movement right and left, up and down. So putting a pin, it will stop. Putting a pin is exactly what I was telling you, putting Superman or Superwoman in there. Right? So it's the top portion is free to sway. Nothing is stopping the top portion. But how do we know whenever we have doubt? Whenever we finish the first moment distribution, right? Assuming that you are convinced that it's not going to move. I'm going to tell you how to find out if you're right or wrong. Right? You go to the first moment distribution. You're going to be able to compute AX. You're going to be able to compute DX and FX. Right? So whenever you do, assuming that you said there is no lateral move, whenever you finish first moment distribution, you're going to be able to compute all these reactions, AX, DX, and FX. If there is no lateral movement, when you do summation of forces in X, AX plus DX plus FX, what does it have to be equal to? If there's no lateral movement? Zero. But if there is you do summation force in X and it's not equal to zero, what does it mean? Well, that is a different way of finding out whenever you have doubt. You do the first portion and you sum forces. If it's zero, no lateral movement. But if it's different than zero, that's your force P. That's the force that you need to stop the lateral move. Any question about it? And I want to repeat myself because in this exam, 40% of the students solve only for moment distribution number one. They did not realize that there was a lateral move. So the best rule is you compute the forces in X, you sum forces. Another thing, people forgot when they do summation force in X, they forgot this force. You're doing summation force in X for the entire frame. So you have to have AX, TX, FX, and the 30 for clarification. If D was fixed, if this was fixed in the front, remember CD, we consider a wall. CD, no. Really, you don't really understand. Because let me show you something. Let me clarify. So let's just make it it's very simple. Right? This is the traffic light, right? The traffic light or just the light pole. And the wind is gonna which way this is going to move with the wind in the left. So this is gonna do something like this. And we call this the deflection. And there's a wall here at the bottom. I'm gonna do something else. Now I have put a frame and the wind again blows in there. Two columns. Gonna move to the left. So this is your size way. So it had nothing to do with this support. It has to do with the top. So how do I stop this? Like Moses suggested, I put a pin in there. By putting a pin, I'm putting a force. I'm putting a force in here to stop this. And this is what we're doing with this problem. So remember, the easiest way is when you finish the first moment distribution, because no matter what, you had the same load but replace the bottom support with pin, but still, yeah, yeah, definitely. What we need to stop is the sway of this point or this point. Exactly the same. Exactly the same. This is the bottom. It's not gonna move to the left, it's not gonna move to the right. But in here it still moves. Exactly the same. So what I was saying is that whenever you are not sure, some programs they are difficult because we have not developed a physical feeling of what this structure is doing. A physical feeling of how it's going to move. So you assume that there's no size width. Don't forget AX, DX, FX, and this 30. If that is not zero, that means that you need a force P. And that is indication that there is a lag. All right. Any other question? So definite, this is indeterminate, and definite, it had a lateral movement. We need to find out A, B, B, C, C, D, D, E, and E, F. I'm not going to put the whole thing. I'm just going to put fours and three. A, B, four or three for this member. Or E, I, or L. B, C, C, D, three. C, E, and finally E, F, three. What was difficult in this problem Fix a moment. Fix a moment were difficult in here. I'm going to tell you why. For CD, remember CD, can I use this case? Fix and pin. Can I use this case in here? Yes or no? And my load, look at my load. My load is going to the left. The same as this one. So my moment at the top of my column for my problem is going to be positive or negative? Negative. Good. Negative. Good. So to compute the moment, I'm going to use this formula. Remember, no matter how short or long it's always A, and this is always B. The next one is a problem. Look, this is wind uplift. I gave this wind uplift and people still consider it was going down. Right? Like before, we had in another problem broken into a rectangular and a triangle. So now I'm going to fix this end. So each one of this is WL squared over 12. So it looks like this. On the left, clockwise. On the right, counterclockwise. Is this correct? Or I need to reverse this direction? Reverse. Okay. This is what we have. On the left, clockwise. On the right, counterclockwise. Is this correct? Or I need to reverse it? Okay, we are tied 1-1. Anybody else? You know that's difficult. Look at the direction. This is going up. So I'm turning this page. This goes up. This one in the direction of the 4. The only thing that I'm doing, look, when this force goes down, the one on this side is counterclockwise, the one on this side is clockwise. The only thing I'm reversing the page. Now the load doesn't go down, goes up. So this one is the one on the left. What direction is that? Clockwise or counterclockwise? What is this? So this one is clockwise and this one is counterclockwise. So clockwise and this is counterclockwise. Now let's look at the triangular shape. Triangular shape going up, and here is clockwise, counterclockwise. So which direction gonna be here, clockwise or counterclockwise? This one. For the triangular load. There. So the value I need to put in here is W squared over 30. And this is W L squared over 20. So this and here is the same. I'm having this. So the only thing that you need to do, you need to rotate this table. So that was difficult. The computation of the fixed and more. Yeah, I think that somebody is recording it. There's always somebody. So remember, last year they had 2.5 hours. Problem number 1 was short. Problem number 3, you used number 1 and was short up to the last point when you set up the integration. This was a long problem. Right? You already told me 4EI, 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 3EI, 3EI. I had it here, joint B. I had joint E, 4EI over 15 divided by 4EI over 15 plus 3EI over 15. Why I don't show it in here? Why I don't show joint B? Look, I'm doing the computation for joint E, 4EI over 15 over 4EI over 15 plus 3 over 15, 0.31, 0.69. Why I'm not doing joint B? Anybody? 0.5. 4EI over 10, 0.5, 0.5. And join C and do it in here. Normally, extended of only members connected to E. To E, there are 2 members. To B, 2 members. To C, 3. So I'm gonna do the E join C in here. we want to start with the one on the left, CB, from C to B, 4EI over 10. We had three members framing into joint C, 4EI over 10, 3EI over 15, 4EI over 15. They are in here. 4EI over 10 divided by the summation of stiffnesses, all the members framing into 3EI over 15 of the summation of all the members framing into the joint. And after that, the last one, C to E, is equal to 1 minus the other 2.31. This is what I was telling you for the fixed moment. Direct curve over 12, direct curve over 12, direct curve over 30, and over 20. This is what I just did show it to you, how to compute the fixed moment. This is superposition. You have to be careful with the direction of the moment. And I'm not going to assume there is lateral movement, but I'm going to assume that I don't know that there is lateral movement. Right? This is the table. Joint A had one member. Joint B had two members, each 1.5. Joint C had three members. We already computed this thing. Joint E had two members, and joint F had one member. So if you look at the moment that we computed, we have C, CE, and EC. We had these two moments. We had this moment with this and this moment with that. So the one on the left, remember CE, the one on the left is positive or negative? What sign is for this fixed moment? Positive or negative? And the other one is negative. So you had in here CE, CE positive, EC negative. Very common mistake. People reverse the sign, negative and positive. And CD, computed in here by using the equation by using this equation. So the table, like I said, people made a mistake with the sign and also computation of this moment. We had to go through one cycle of moment distribution, and this is what we do. This is exactly what I did for problem number one. We had gone through one cycle of moment distribution, and these are the moments at the end of the member. So those are the moments at the end of this member. And column AB doesn't have any load. Column CD had a 30 kip to the left. EF doesn't have any load. So I'm going to do for column AB, my free body. You look at AB, moment AB 1517. Positive, clockwise or counterclockwise? This one. Anybody? Clockwise. And 30 BA 3033 also clockwise. So my shear force in here is gonna go the bottom to the right or to the left to have equilibrium. Which direction the one at the bottom? Right or left? Right. And this goes to the left. And this distance is 10 feet. So I could compute this in here is 4.55. So I had done this in here already for you. Column AB, DC with a 30, has to put the load in this exam. Many people forgot to put this load in here. You have to put the load because it's there. So I had computed these forces. Every time that we had the moment, we could compute, and we need these forces to do our shear diagram. So with the moment that come from this table, we can compute these shear forces. And we go back to our frame. And we put these shear forces in here, 455, 1151, 47. And we do summation of forces in X. And it comes the P, 33 point. What does this mean, 33.10? Do I have size weight or I don't have size? If I had a P or different than 0, what is the meaning of it? Look, I'm doing just one moment distribution, the shear forces. The shear forces come from here. So I went back and I put the shear forces in here. And I did summation of forces in X. P equal to 33.3 means that there is a size weight. So I have to do a second moment distribution. And so I assume in here, because P goes to the left, I have to consider Q in the opposite direction. So P came to the left, Q goes in the opposite direction. And so we had a delta, delta, and delta for the column. Since this is fixed, there are two moments. Pin fixed, one moment. Pin fixed, one moment. So what I did for AB, I assumed that was equal to 100. And like I said before, you cannot imagine how hard it was for us when we were students without any calculator, no computer, just a slide rule. You couldn't make a mistake. You had to be paying attention before we put a number in our slide rule. We knew the answer, know exactly how close. So we used to smell the answer. We couldn't afford to make a mistake. Now you made a mistake and you do correct it with your calculator. Can I put Q adjoin B? You can put Q adjoin B, adjoin C, adjoin E. And this is a good question because everything goes back to the foundation, to what you have learned in static, mechanical, solid. But since we are not computer, we are limited how much we can, yes, a sliding vector. It read my mind. The force is a sliding vector, can be put anywhere along the line of action. So Jeremy probably had taken static 3 or 4 times because he had good memory, or he had a good memory. Anyway, this is the reason anywhere in that. Why would you assume P to the left if the 4 or 30 is also to the left? I might be blind, but Marisa, why would you assume? Marisa, is this left or right? Marisa, left. And what is it? Right. So I don't have to assume anything right now. I don't have to assume anything because I already know P goes to the left. Q is always in the opposite direction. So even if they torture you, you are certain that this is correct because P is correct, Q is correct, always in the opposite. Any question related to that? Okay. So remember, P and Q always opposite direction. So in this case, we are not assuming anything because we were not certain. We were not certain if we had lateral movement. So I told you, now you know you do submated force in X, we had lateral movement. So this lateral movement is stopping the movement trying to go to the right. Now I'm putting in, and the answer is correct that anywhere along this line of. Sometimes we put it in a place that is not going to be covered by the movement. But delta, delta, delta the same. I was saying that you are privileged because you have calculator. We always assume a large number to start with. And this is 6EI delta over L squared. This is also 6EI delta over L squared. We could compute that, but we don't have to because it's given in the table. Here at the bottom. If the column or the girder moves in a clockwise direction, the moments go in a counterclockwise direction, and both of them, they are the same. In terms of delta, both of them are 6EI delta over L squared. So if this is 100, this is 100. In terms of whenever we had a pinwheel roller, it's only 50%, 3EI delta over L squared. So in this case, I'm calling this one 100. So this one, and we don't have to worry about the sign right now. We know the direction is opposite to the movement of the column. But I'm saying 6EI delta over L squared. For the first column is 10 squared. This is equal 100. So this is 6EI delta over L squared, 6EI delta over L squared. Both of them the same. So since all of them, the common denominator is delta, I'm going to find delta is equal to 100 times 10 squared over 6EI. So from here, I'm saying that delta is 100 times 10 squared over 6EI. And we leave it like this. because now I'm going to go to this column. The fixed end moment, because this is a pin only one, I'm going to call that one the fixed end moment from C to D, 3EI delta over L squared. And the L, and there is 15. Why? Why for CD and using 3 and not 6? Anybody? Why I'm using 3 and not 6 for this method? Okay. Excellent. So now I'm going to relate delta is the common denominator. So I'm going to say this is equal to 3EI over 15 squared times delta. 100 times 10 squared over 6. Just practice while I rest a little bit. Tell me what you find. What is it like? Check your calculator for the exam. Practice. Tell me what is the number. Don't read it from don't read it from the screen. Just do it. Computation. Okay. Yes, Lee. Just a minute. I want you to somebody to give me that computation. $22. So that's correct. So now you know why these are 100 and this one is 22. And the last one I'm going to do here before I answer your question, the fixed moment from E to F is equal to 3EI delta over L squared, 5 squared. I'm going to replace this 3EI over 5 squared and give me a. So I'm replacing for the little column, I'm replacing the delta, and I'm going to obtain 200. Right? So this is the reason why these moments are not the same, because the column have different height. The column has different conditions, a pin and a pin. Now there's an interesting question from Lick. He say, how do we assume a positive or negative? We do not assume. We cannot assume anything right now because we do know. We are not assuming anything because we do know that P goes to the left and Q goes to the right. If Q goes to the right, all these columns, they're going to move in a clockwise direction. So we are not assuming anything. So this goes, he's asking about the sign, right? So the rotation here is clockwise, clockwise, clockwise. The rotation here is clockwise. Look, it was at this location, it moved down. So this is in clockwise. The moment going the opposite direction, counterclockwise. And this direction leak is positive or negative? Positive or negative? This direction. Negative, okay. So what are all of this? Positive or negative? Negative. And why? I'm not assuming anything because I know that P goes to the left, Q goes to the right, the column, I'm going to move clockwise, the moment go in the opposite direction. If you assume P to the left and it was negative, will you just change the direction and just need to go in the other way? Okay. Now, this is a good question. It came from Moses. Look, when I start this problem, and I decided that I'm going to assume that it move to the left, right? If I assume that they move to the left, my moments, they're going to go for the second moment distribution. The moment is going to go in a clockwise direction. If I assume, right now, if I assume that it goes to the left, my moments for second moment distribution, they're going to be positive. When I solve when I solve for the problem and he told me that this goal is in the opposite direction, the only thing that I need to do is reverse the direction of the moment. So I'm correcting that. I don't have to put a negative sign in the P over Q. I just reverse before, since I made the wrong assumption, I just reverse the direction of this. If we assume wrong direction, I'm accusing because I am. No, you have to be careful because the P over Q is going to come with a negative. So P and Q, you have to be careful. You got to put a negative in front. So it's better to change the moments in your moment distribution table. Any other question about this? So with the second moment distribution, these are the fixed moment, fixed moment, fixed moment. You find the moments at the end. And you use this moment from the second moment distribution, you use this moment to compute the shear force at the bottom of the curve. No low, no low, no low in between. So this computation is very simple because the moment divided by the height, the moment divided by the height, the same. And you do summation of force in X, Q 25, 23, P over Q, this is the ratio. And in this table, I have multiplied this by P over Q added to this value. Multiply P over Q added to this value, and I obtain this. P over Q with this value give me this. So these are the moments at the end. And from here, you do your free bodies and you do your shear moment. So obviously, this exam, they had 2 hours and 30 minutes. So most of the time was spent on this problem. They had to make the decision which problem to solve first, which problem to solve second, and which one last. In the exam, I'm making the decision for you, so you don't have to worry about that decision making. Any question? Because I'm tired. Any question? So why do we start here from joint E in the table? We start from joint C in the table, joint A in the table, joint C in the table. And let me go back to this. Are you talking about this problem? You talking about this joint? Where do we start? Yes. Okay. Look, there's only one choice. There's only one choice in here. The moment is going to be at the top, and this is going to be a pin. So there is only only one choice, moment here and no moment here. Is that what you're asking? Because if I understand correctly, you can always start. Okay, now I know what you're asking. We're using this case, right? And if I understand correctly, you're saying that we could start with this one too? Is that what you're asking? Lick. Is that what you're asking? No. So what are you asking? Distribution table. Oh, this table. Hmm? Yes. You can start any joint that you want. In this table, for instance, joint C has in here these two moments. You can start at joint C, you can start at joint E, you can start at any joint that you want. So sometimes in very few problems, it makes a difference. If you start at one joint, it goes faster than if you start at a different joint. But you have to put all the joints in equilibrium. At the end, every single joint has to be equilibrium, summation of moments equal to zero. So you can start at any joint that you want, because at the end, all of them, they're going to be in equilibrium. Does that answer your question? Okay. Any way you set up, yeah, I know what. Any other question? Remember, you can set up the table any way you want, but every joint has to be in equilibrium. You can start balancing any joint that you want. Any other question? Okay, no question. See you, most of you, on Monday. Be there on time during the weekend or tomorrow or tonight. You have any question, just let me. Well, good luck. Hopefully, I don't have to see you again. Bye bye. You are. Yeah, me too.